morning, good afternoon, and good evening, wherever you are. Thank you for joining. At CIQ, we're focused on powering the next generation of software infrastructure, leveraging the capabilities of cloud, hyperscale, and HPC. From research to the enterprise, our customers rely on us for the ultimate Rocky Linux, Werewolf, and Apptainer support escalation. We provide deep development capabilities and solutions, all delivered in the collaborative spirit of open source.
All right, cool. Hey, everybody. Thanks for joining us live on CIQ's YouTube page. We are so excited to be here wherever you're watching. Welcome, welcome. My name is Rose Stein. I work at CIQ, and we are here to talk about scalable computing. And so what's actually really fun, and this is probably my favorite part of the job, is when something will seem like, I'm like, oh, what exactly is that? Is it this or is it that? And then I go and I ask any of the engineers like at our Slack channel, and there is differing views even on the same topic. And that is probably like the most exciting part to me, because then we get to define what it is that we're actually talking about here and like really dive into the importance of this particular topic. So Jonathan, thank you so much for showing up. It's good to see you.
Good to see you too, Rose.
Awesome. And Brian, welcome.
Hey, good to see you. Good to be back on the webinar, Rose.
Yeah, it's really good to have you. Okay, so the first thing we might want to just kind of define, because when we're talking about scalable computing, there seems to be just like a couple different ideas out there on what exactly we're talking about. So let's hone in and really define what it is that we're going to be talking about today on this webinar.
Yeah, so there's like the discussions that we had in prep were divided on like two different contexts. There's scalability of the infrastructure that you're running on.
Oh,
yeah. Hey, Gary.
Hey, Gary. Welcome.
Hey. Hi.
Okay, cool.
Yeah.
I think the audio
Yeah, there's scalability of the infrastructure that you're running on.
Oh, no.
Gary, I think we're getting echoes from you. There we go.
Maybe I'll mute too while you're talking.
Hey.
Oh, it is you, Gary. Gary, you're echoing in. You're doing like a wah, 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 wah.
Yeah, I hear a lot of echo. I'm not sure why. Sorry about that.
When you talk, it actually sounds fine, but then when we're talking, it sounds weird. So yeah. Maybe we'll just have you on mute until we get to you, because you sound fine when you're talking. So hang on a second here, Gary. I'm glad you're here though.
Yeah, so there you can talk about the scalability of the infrastructure you're running on, and two areas that we were discussing that in were, there's scalability from an on-prem infrastructure out into the cloud, let's say, and that's one way to look at it. Another is scalability of your physical infrastructure and how easy it is to expand that infrastructure. Both of those are kind of predicated on the assumption that that there's this imagined infinite pool of resources that you can grow into, either by deploying new equipment locally or utilizing public cloud infrastructure. The other major part of the conversation that we had was about applications being able to scale out and use the infrastructure that you have available. And so within HPC, we usually see this through the use of MPI codes to do distributed and distributed memory computing. But there are others, like in the high throughput computing space, you can just do embarrassingly parallel algorithmic work, or there's other alternatives to MPI. One that we've been using or working with recently is PGAS and the GasNet protocol as part of the Chapel programming language and others.
Awesome. Thank you for that, Jonathan. So what is it, Brian, that we are going to be focused on today in the topic?
Today, we're going to be focusing on, I guess, in terms of scalability, we can talk about scalability from an infrastructure perspective. And to add, I'd like to add one more point to Jonathan's point. So in the CFD world, there's also scalability of like your model as well that you're running. So if you have a extremely coarsely meshed model and you distribute it across a lot of nodes, the performance will taper off the more cores you throw at it. So if you have a bigger problem, if you basically have a finer mesh with a lot of points that you need to run simulations on, throwing more cores at that finer meshed model will yield better scalability. But for today's topic, we will talk about scalability of the system in software. Yeah.
Did you have something you wanted to add to that, Jonathan?
One of the things I was thinking as Brian was discussing, like the scalability of a model, is that often, and forgive me, Brian, if I'm reiterating just part of what you said, but when you talk about how scalable a model is, you will often see a point of no return or limited returns on it. And so when you're assessing how scalable a given code or a given model or a given algorithm is, often you're talking about how far you can scale it before the communication, let's say, the work of doing the scaling becomes dominant in the computation, and you're not able to scale to a larger system at that point. So both of these are important in the general conversation. There's no point in having a larger system if your code can't take advantage of it, and there's no point in having a scalable code if you don't have a system large enough to accommodate it.
Thank you. So it works together. So it sounds like a bit of planning, like forethought of knowing where you're going might also be helpful, and what it is that you want to do with your system and your code.
Yeah, absolutely. In environments that I've worked in the past, it's been like general purpose university or other kind of, there is a system and it's used by a variety of different researchers and research areas, and that sometimes makes it difficult to do that kind of planning. But in the best case, when you know the kinds of applications that your researchers are going to run, you can see how scalable those applications are and design a system directly around that. And then if you have software developers working on that algorithm, working on that application, they can take specific advantage of the characteristics of the system that they're on. So it's always a back and forth and a planning exercise in the best case.
Gary is back.
Yeah. Can you hear me okay?
Yeah.
Yeah, it's great.
Yeah, okay. Sorry about that. Yeah, for some reason, I just need to reboot my machine.
You say for some reason, but it happens often with all of us. Like, just got to like work out the kinks. I mean, the brain is the same way, right? As being a person. Like sometimes I just need to take a step away. So anyway, glad that you're back, Gary. You want to introduce yourself and talk about how scalable computing relates to what you're doing at Berkeley?
Sure. Yeah, my name is Gary Jung. I manage the institutional high performance computing effort over at Lawrence Berkeley National Laboratory. And I also manage the HPC program down at UC Berkeley.
Wow. Never a dull moment in your world, huh?
No.
So we were actually just talking about thinking ahead, right? When you're thinking about scalability, like not only of your infrastructure, your system, your software, like, all these things kind of need to work together. And the idea that we need to like think ahead, right? So I imagine that LBNL and UC Berkeley are similar, but have some differences. So when you're thinking about their systems and their compute systems, like what are some of the similarities and differences in terms of their forethought in scaling and maybe even some of the trouble that they've gone into not thinking ahead enough?
So for us, I usually think of scalable systems as building blocks. And I don't know, I don't want to repeat anything that I don't know if anybody has said this already.
I think you're going in a new direction. It sounds great.
Yeah. We think of like an infrastructure that you can scale out using building blocks.
Yeah.
And so usually what you have to do is there's a lot of planning in the beginning in terms of how big you might eventually want to see the overall structures, because then that really depends how you're going to set up the backbone for the InfiniBand fabric, or how much you're going to scale. So usually the questions are like, ultimately, how far do you want this to scale, or how much do you want to plan for scaling it out, so that you don't limit yourself in terms of how you set up your infrastructure. So that's usually the way we set this up. And what we do is we tend to build the two different environments, the Berkeley lab and UC Berkeley, the workloads are different between the two. Maybe one way I can generalize it is saying that Berkeley Laboratory does large team science, so the projects tend to be bigger and the codes tend to be more, let's say, capability based, because they're larger projects and sometimes have larger compute requirements. But the way we think about building the systems is still similar, and the systems just may differ in terms of whether you scale more network into it or how much performance you build into the system. So I'll leave it at that. But when I talk about scalability, we're talking about building something with building blocks and ultimately how you design the infrastructure for that.
Gary, if Rose, if I may ask a question here. So when you're doing that, it helps to know that you have kind of different known and maybe not well characterized, but at least some characterization of a differentiation between those two environments. So that speaks to being able to look at that workload and plan the environment around it. But what variables go into your expectation of how far you'll want to scale a given environment before it's replaced by a new one? Is that a look at historical trends and how the compute load has grown over time, or is that an individual exercise with the researchers that are on it? What does that look like in your environment?
It's we've done it mostly by historical trend, because a lot of times you're thinking about how much capacity you're going to have. So we do gather research and input, but we provide such a support for diversity of research that it's hard to build for any one. So we tend to build more generalized infrastructures. It has to be pretty good in most dimensions. Then if you're going to build for a diversity of research and applications. So then the things that are taken in consideration are budget, things like physical limitations such as data center space and power. That might be another consideration for scaling. They tend to be more of those types of things. They're more the constraints than let's say the system performance.
Fair enough.
So this is really cool, Gary. I'm so glad that you were able to show up, because it's kind of like you are here with this real world example of the things that you can do when your system, can scale. And then at CIQ, like we empower people, right? Like we're like, okay, like I've been on, calls with Jonathan talking to different universities and different companies. And it's like, okay, well, what is it that you want to do? Right. And okay, like let's structure it this way so that we know that where we are going and what it is that you will need. And Brian and Jonathan, and helping build some structure for people so that they can scale it the way that they want to. So I'm so glad that you're here, Gary, or even Jonathan, Brian. Do you guys could you give some examples of things that are possible because we have been able to scale at such an incredible rate?
I think from scaling from a capacity standpoint, from organizations that are in the automotive or aerospace industry, if a lot of their simulations typically run for weeks to maybe even a month, and their on-premise system will usually fill up. So with the ability of being able to scale to the cloud, they're able to run their simulations there and get their results. And as a result of that, it's possible that they can manufacture their product and actually get to market faster by leveraging the cloud.
Yeah, the best case scenario, that like there's two main things. You either do more work in the same time, or like you either get your result faster or you get more done in the same time, right? And the part of that I am most interested in personally is that getting your work done faster, but that's like from a research background, I think.
Mhm.
I think in a production mindset, if you're in manufacturing or something like that, where you're doing a lot of the same work and it's about throughput, that's one interest. But what I like to see is there's the computation is only one part of the research cycle, right? You put some work into a system and you get some data out, and then humans think about what happened and what they saw out of the computation, or they learn something from it. And the faster you can get that iteration, the more you get to have kind of the human innovation be part of the equation. And so the longer it takes for you to get your result, the more time the researcher has spent waiting and wishing that they knew what the next step was going to be. And so that's where my interest is driving that time to solution for the next iteration of innovation and interest down.
Gary, I imagine too, and this is one of the things I see at, specifically universities is what's popping into my mind, but I'm sure it's other places as well, that people are wanting, especially with Aptainer. It's like, well, we want, and more of our professors are wanting to really utilize the resources of our compute system, and be able to like have their own containers and do things. So when I'm thinking scalable in that sense, it's like there's more and more and more and more and more people wanting to utilize the resources and run jobs. Have you seen that as something that you've had to work on too, Gary?
So you're saying using containers then, or
well, that's the specific example that I am thinking of right now in terms of like scalability. How does that kind of relate to it, where there's more and more people utilizing the resources of the system, like being able to like tap in and run jobs?
Yeah, we recently built a large system. Is a 100 node system for the Joint Genome Institute that's
Cool.
based out of Lawrence Berkeley National Laboratory, and they used to run their workloads at the NERSC National Supercomputing Facility, and recently moved a lot of their work over to our institutional systems, and we built them a specific system for this. So one of the things that about supporting the life sciences work codes, such as at the Joint Genome Institute, is there's so many different codes, and there's just so much work in building the environments to support each one. And so we took a different approach when we built this cluster in that we have it running containers. So most of the people are building containers and submitting the jobs to run as containers on this cluster. And it makes it scaling a lot easier, because now we can essentially not only can they run on our system, but they can essentially run on any system running Aptainer, because now we've essentially are in the process of getting all the users to convert all their applications over. So now they're going to run on a new cluster, and then because it's all container based, it can also run other places too. And so they're going to be running at other national laboratories and other computational resources they have access to. So they are scaling in effect outside the institution, because they have an easy way to do that.
Rose, I really like this idea of thinking of scalability as a factor in computing accessibility. You can think of like the negative degenerate case of, I have this machine right here in front of me and I can do a certain amount of work on it. And the other computers that the rest of you are using are inaccessible to me, and I'm not able to scale my work out to them. One of the things that I really enjoyed doing in a previous site was we built what we called a condo cluster, where historically at this institution, which is not atypical in universities, you'll have a researcher come in and they'll they'll have some initial seed funding or grant funding or something like that, and they'll buy a small cluster, maybe a couple nodes, maybe let's say 16. That's not an abnormal size for that kind of an environment. And their researchers will be able to use those instruments, those resources, and they can scale up to that size, and that's the limit. But our goal in building this condo cluster was to try and co-locate that as a social exercise. So we would help them identify what equipment to purchase and make sure it was all part of one scalable infrastructure. And it was incredibly heterogeneous. I mean, we often think of scalability in this environment that you have a given set. Gary was talking about building blocks, and that you have like a uniform building block, and whenever you scale up, you have more of that exact same kind of infrastructure. This was the opposite of that. Each cluster was almost bespoke, but then it was all part of one shared infrastructure. And the best case scenario there was we had one customer that had real money to buy real equipment, but they didn't have as much experience standing up a cluster, so they brought it to us and they said, "Hey, this is what we want to buy. Is this something you could help us manage?" And we did it as part of this single infrastructure. And we got it up and running, and 2 months before they were actually ready to take advantage of it, in that time, that system was used. I think it was something like 93% utilized for those 2 months, even though the original customer hadn't even touched it. Because the people that were already part of the infrastructure were able to scale out into the other resources that had been added to it. And so I think it's an interesting point that scalability isn't always just about the performance that you can have with the equipment you purchase or what you have made available to yourself or within your enclave, within your group, but it's about making as much of the resources available to as many of the people as possible. And once you have that, computers that sit idle aren't useful to anyone, and the more you can utilize them, the better.
Yeah, I like that. Thanks for that real world story. And it kind of like wraps back into Aptainer or other software that helps people scale in the various different ways that we're talking about. What are some other software that you really like that is helpful for that as well? Everyone's kind of like looking up, thinking. Brian,
Yeah.
You got one?
I like Fuzzball.
Well, that's a good one. I think we're familiar with that. So Fuzzball actually uses containers as well, correct?
Yes, that is correct.
So how could that help companies scale? And what part of scaling are we talking about that Fuzzball can help them do?
I think with Fuzzball Federate, I think from a capacity standpoint, it could help orchestrate an organization's workflows on, I guess, the optimal hardware, or at least where there is capacity. And I guess it would depend on what the organization's doing. The particular use case I'm thinking of is genomic sequencing, where you're just trying to get the throughput of sequencing as many samples as possible to get, if you're looking for VCFs or something.
Yeah, and part of that is it's just the next step in this entire conversation of making the scalability available and accessible to people. And Gary was talking about the benefits that he's seen with people around him in having their workload containerized, and running it that way locally meant that they were portably able to scale beyond the local environment, because they can take the work that they did and prepared and run it in other environments as well. And that's true pervasively with containerization and in particular with Aptainer in the HPC space. But that's the exciting part about Fuzzball to me, is that it makes it even easier to take that work that you containerize. That's not a whole new way of doing things. It's building on that experience that we've had, and the benefits of containerizing it, making it portable to a number of environments, including Fuzzball, but not even exclusively Fuzzball.
Awesome. So it sounds like there's a lot of different things that we can do, and feel free to correct my terminology and my words, but like the basic idea is that you can scale up so you have more like compute power within the infrastructure that you already have, or you can scale out where you actually have more computers, servers, nodes, clusters, whatever it is. You can also, there's also different software and applications that you can use to speed things up, just as you guys were saying. So the data that you get back, instead of it, taking a month to process, it only takes a week, an hour. Okay, maybe I'm going a little wild here, but right, there's shorter and shorter time to get the results that you are looking for. You can do more. And then there is also the scaling in terms of allowing more people to have access to the resources that are available. Does that kind of sum it up? Nods.
Yeah, I think so. Yes.
That's the basic gist. Awesome. So what are some of the limits that impact scalability in HPC? I mean, we kind of touched on this, but just specifically.
Yeah, and my experience mirrors what Gary was talking about, that often it's about power, cooling, and budget more than anything. But my experience is similar in that it's in that kind of a general purpose environment, where you're trying to build something for the common case that makes it available to the most people. In theory, there are also limits on what your algorithm or your code are able to do. But power, cooling, and budget tends to be where you actually find your limit first these days.
Yeah. So you can do anything with the right amount of money, huh?
Mm-hmm.
That's good to know. Brian, did you want to add to that?
No, I think those are the main limits that I've run into from my experience as well.
Yeah.
Although, what we've also talked about is just access to the equipment too. When things are partitioned out, when you don't have the ability to get your code onto it, like from the user's perspective, that may be even a bigger thing. We would run into people all the time that didn't even know that we had an HPC infrastructure, and we're running things just locally on a machine. So, the same conversation we've been having applies there as well. Sorry, Gary, for speaking over you.
Oh, no, I was just agreeing. It's probably the thing people run out of money first is run out of the people. The thing that people run out of is money usually. But there are times where certain codes won't scale beyond a certain number of nodes or something, and this really has to do with the type of code it is. And so there are limitations to certain applications.
All right, what are some best practices, Gary? You've got a lot of experience in different fields. You do a lot. So what can you share with us about best practices in terms of scaling in the variety of ways we've talked about?
Yeah, just planning for it, and then planning for scalability is important. So thinking way ahead about how you normally, when you buy your first system, you're thinking about a lot of times people are thinking ahead, like, okay, I'm going to start with the system, and it's going to get bigger when I get more funds. And so there's always a decision point about how much should go into the infrastructure and how much should go into the resource itself. And so there's and you have to make sure you don't limit yourself in terms of like what you choose for the infrastructure. So you don't make decisions that are going to limit you later in terms of ultimately how large the system is going to scale. So there's a lot of architectural decisions that have to be made when you do a scalable system. The other thing that people don't pay as much attention to is the performance of a scalable system. And so a lot of times people will start off with a small system, and maybe they'll benchmark the small system and they'll say, okay, great, I'll just buy more of these. So they'll just assume that they could just buy more of these and put them together and it's all going to work. But it is important to go back and benchmark and make sure that you are getting the performance that you had intended out of the large system. So that's a step that a lot of people don't pay attention to. And so we'll get large systems in, and we'll benchmark them, and the vendor will say, well, we have tons of these in the field. And I'm like, well, how come nobody's seeing these problems? And they are real problems that we find. And it's just that people don't do the due diligence to check how the performance of the overall system. And that's worthwhile to do, because you want to make sure you get your money's worth. You can deliver the performance that you thought you were going to get.
Right. Yeah, that totally makes sense. That say you got all the money in the world, but if you just keep adding and adding and adding and buying more, but it's not working optimally or efficiently or the way that you expect or need or want it to, like, you can pile things on and it's not going to do you any good.
No. Yeah.
Yeah, that makes sense. I do want to say, because, we are live. So if you guys have questions, feel free to pop them in, and we'll have one of our people put them up on the screen here so that we can answer your questions. I mean, we are here. We are definitely live, and we are ready to be helpful.
Yeah, I was just going to say
Brian-
something. Brian mentioned something about scaling out to the cloud. I do want to make a pitch for that. Depending on the application, we found a lot of applications that need to scale or have, the demand for it is just at certain times. Then the cloud works out really well. I mean, you have simple tools like the ability to, like, say, auto scale with the cloud instances. That makes it perfect for, like, say, doing a release of new data or something like that, where everybody's coming to the site and they'll just overload your on-prem. It's hard to design an on-prem system for something like that, where you're going to design it for the peak load. And so that's a perfect use case for, like, the cloud, is that you can build an infrastructure to do that on the cloud. So I would bet a lot of the people doing streaming video, movies or whatever it is online, they, it's going to be busy around, like, the holidays, and then people are off, and then quieter other times. So it makes sense for people like that to use the cloud.
Yeah. Thank you.
Do you see much of your computation scaling out to the cloud, Gary, or are you seeing that more as a service offering when you have things that are consumed more by a general public audience?
We do use a lot of, right now, a lot of stuff on the cloud is not used for scaling out, but it's really more for getting things up quickly. And it just has to do with, when you start scaling out, then the cost of the resources are expensive. Mm-hmm. And we don't have as many use cases where people just have a short project and are just needed for a short amount of time. So then it's more cost effective for us to bring it back on-prem. We'll see that people will start to scale out, and then they'll see the cost, and then we'll bring it back on-prem.
So it would be really cool if there was some kind of software that could know your on-prem resources and know your cloud resources and kind of delegate these things appropriately based on what the job is.
That would be cool, wouldn't it?
I think that would be cool. Brian, what do you think?
I think Fuzzball Federate should be able to do that. Reach out to us if you're interested.
That is definitely something that we come across, right? And in just total organic conversation, it's like, aha, there's a problem, let's solve it. So yeah, that's definitely one of the things that Fuzzball can do and is doing.
Yeah, and it goes back to the accessibility conversation. One of the biggest impediments there is that often running in the cloud is operationally very different than running on local infrastructure. They're culturally different, they're infrastructurally different, managing them is different. And so one of the goals of Fuzzball is to make that more similar. That if you have a user workload that's already containerized in the same way you would do with the standard Aptainer environment, you can take that workload and run it in the cloud or on-prem, and it feels exactly the same. And you don't have this portability problem of taking your workload that works in one environment and now you have to convert it to another because the cost-benefit analysis shifted a different way.
Yeah, I'll add one more thing to that. And I think one thing nice about Fuzzball Federate is that if you're using resources at multiple institutions, for example, then you don't have to worry as much about the points of integration between the two infrastructures of the two institutions. And because Fuzzball Federate just sits at a level that's a little bit higher, doesn't require all the low-level integration that you would when you're sharing data and stuff between two institutions.
Yeah. All right. What about you guys can keep going on this topic if you want to, but I'd love to hear some more best practices or strategies, best practices that you've come across that you'd like to share.
I was going to say automation, because the least scalable thing in your infrastructure is the people. And so the more that you can start out anticipating that future scaling and using your smaller system to iterate on getting things automated, getting things replicable. If you don't do that at the beginning, then as things start to scale up, it's just you're going to have a mess of one-offs and by hand configuration. And so, we've had a lot of benefit there historically through the configuration management practice. There are a number of products there. Within CIQ and I personally, we tend to propose stateless management of your infrastructure whenever possible. And so that's how the Werewolf system would help manage this kind of scalability of having a single node image that gets deployed out to all of your compute infrastructure. And then there's work going on to try and unify those node images that you might deploy locally with what you might see in a cloud environment as well. So just getting as much of you can as simple as possible so that it can be automated, replicated, and scaled out and up whenever necessary.
I think for me, I think a lot of times users hit the limit of not knowing what they are able to do on a system, and to kind of address that, just having good documentation so that the users can help themselves, and that would lighten the load on the administration team so the administration team can actually focus on building the users a better system.
Yeah. I like it. This is all really good. And I imagine that any admins out there thinking about this, they're like, thanks for the suggestions, guys. That takes time.
Yeah, but honestly, like we're talking about products that we have here at CIQ that people might be interested in. There's also just consulting and services that we're able to offer too. And if any of this sounds like interesting but you need help, still get in touch, because whether it's with one of our products or not, we have a lot of HPC experience here, and we would love to work with you, love to talk with you about your infrastructure, what problems you're having, and how we might be able to help you with a solution.
Yeah. Agreed. All right, guys, is there anything that you want to add? I think we kind of covered most of all the things that we wanted to talk about in terms of scalability. I don't believe that there are many questions from you guys. We must have made you speechless with all this amazing information. So I just really want to thank all of you guys for showing up. Do you have any closing remarks, Gary?
No, but I appreciate that Jonathan brings up the fact about that system administration is hard to scale. So it is worthwhile putting in the time to make sure that you use practices that make the best of the labor. And that was originally the motivation for building Werewolf, is that the original project that was used on was at Berkeley Laboratory. We had to stand up 10 standalone systems, and we said there is just no way that we're going to do 10 standalone system clusters and manage them all as individual compute nodes. And so Werewolf was used for that back in 2003.
That was a little while ago, man. I think Werewolf has changed a bit since then. But are you guys
Yeah,
on?
that was the original one.
That was the OG.
Yeah, original. Yeah.
So, what version of Werewolf are you guys using at this point?
I guess we're deploying the current version on our newer infrastructures. We have something that was we had Werewolf, I guess version 3, but it was modified with a lot of the kind of hand modified to have a lot of the features of version 4. So I'd say we have an unofficial version 3.5 on some of our infrastructure, and
Sure.
Yeah, I hear that, Jonathan. You probably hear that a lot as well.
I mean, it's the nature of working on Werewolf while you're using it, is that you're always on an unofficial fork of a little bit more than what's currently available. One of the things I've really enjoyed about it is that it's a relatively accessible code base. So, we're interested in getting people invested in the community and involved in the community for sure around Werewolf. But it also is a really flexible tool just in your environment. It's easy to modify, easy to manage.
Yeah, love it. Okay, Jess, it's definitely question time, so put them up. I just love to. So we got off on the Werewolf tangent. We were talking about other things, so that's definitely something we can help you guys with too. All right, Igor, what's up, Igor? Thanks so much for being here. Do you always build the best and fastest servers? And how do you know what the capacity will be in a few years?
I'll say that when I was last doing this calculation, what we were looking for was performance per watt, generally speaking. We were looking to see how much, like, when selecting a CPU, it was either budget dominated and then you were looking for performance per dollar, and maybe that would mean you spread out to more systems, or power and thermal constrained, and then you're looking for performance per watt. I expect, Gary, you have thoughts on this as well, and probably more than I do on predicting capacity in the next few years.
A lot of times you look at performance per dollar, and then, but one of the things I do pay attention to when we're not necessarily picking the fastest processors, for example, for the servers. We tend to, a lot of times, limiting factor is a memory bandwidth. So we try to get maybe a little more conservative on a processor, but we make sure we get the best memory bandwidth, because once you start taking the bandwidth and dividing it by the number of cores on a node, then it ends up, then you can see how much bandwidth you're getting per core, and that's a really important number for a lot of people. So that's something to look for when you do that.
Please.
Go ahead.
Okay. On a more kind of subjective metric, like the question is the best servers, and often you'll look at a given vendor and there will be different tiers of SKU, and in HPC, typically what I've seen is that you don't deploy like the top tier enterprise big iron server. You're looking for where the economies of scale are, and these days those tend to be the servers that are targeted at the hyperscalers, at cloud scale things. So what's pretty typical these days is a form factor that's 4 nodes crammed into a 2U chassis, and pretty much every major hardware manufacturer has those, and I don't think anyone would consider that the best server in a given manufacturer's product line, but it is the most cost effective, both from a power and cooling perspective and a literal cost perspective, and that's where most HPC, kind of the general middle of HPC, tends to target, in my experience.
Yeah, one thing I will say is that when you're designing infrastructure, sometimes it does make sense to purchase at the higher end for the infrastructure, because the infrastructure tends to outlast the compute nodes, and so that you have to think about making sure that it's going to not only work for this generation processors, but maybe the next 2 generations of processors as you add into a system.
He said, did he say a few years? So
Yeah, the last question had a bit about how do you plan for this, what will be available in the next few years, or what will be required in the next few years. And
yeah.
we talked a little bit about that. There's historical trends in terms of what's available. You maintain pretty close relationships with your vendors and their suppliers to understand what's coming down the pike.
But Gary, did you say that the infrastructure would outlive the nodes? Is that what you said?
Yeah. So
What does that mean? Like
usually, in a lot of settings, but this is especially true in an academic research environment, people have a limited amount of budget to buy a system. And so they will buy it with the intention that they will buy more when they get more money. And then so if you're going to do that and scale it out, and it's going to last for a long time, you're going to use it for years. You're not planning to retire the whole system. You'll have an infrastructure of like a InfiniBand backbone and and storage that's going to go across your compute. Those things is worthwhile paying attention to buy at a higher performance, because it's going to have to scale for one, and then the other thing is it's going to have to last more than the life of the original compute nodes. Otherwise you're going to be, it'd be really expensive to buy compute nodes and infrastructure every 5-6 years or whatever you use for your compute
so
nodes.
is that typically how long a compute node lasts? Is 5 or 6 years?
Yeah, I wouldn't. Yeah.
Cool.
That tends to be the longest that manufacturers will warranty them for and service them for, without special exception.
Cool. All right, we're ready for George's question. Thank you for being patient, George. Okay, how do you identify the bottlenecks that affect scalability?
Run an example application and observe its behavior, really, and run it at different scales and see at what point that performance curve tops out. If you run it on twice as many nodes, do you get twice as much performance? If not, which things are filling up? Gary, what's your experience here?
Yeah, that's the way we do it, and monitor it.
Yeah.
So you just have to have a lot of monitoring in place so you can see where what is running out of resources.
Do you do that from a systems perspective typically, or do you do it with like an application level profiling?
We do it at a systems level, not at applications. Unless we're having a problem with something specific, then we'll start digging in.
I feel like I'm always looking for better tools on this front, and I've never been super happy with my process here. It always feels a little bit up in the air and just a research project every time.
Is that something that you can automate as well?
The collection of it, yes, but the determination of it tends to be a manual process. At least that's my experience.
Yeah. Okay. Oh, Dave Dickerson, what's up, man? How do you account for either tiers of storage, offline storage or tape, or low-cost S3 storage providers as data grows? What has been the best case realistic scenario that you've seen?
So the best thing that I've seen that incorporated tape as like a data archive for users was one where that process was transparent, because people are bad at managing their data between different tiers in my experience. And there are some exceptions to that where there's very explicit, like you're working on a project and that project is done, but the data must be retained and that project gets archived off. So if you have really strong policies around that kind of thing, you can do that. But historically, what I've seen is tiered storage really only works when it happens in the background. and the user doesn't have to think about it. And that's from like a cost perspective, where less recently used storage goes off to tape and people don't have to worry about it, but then they can get it back transparently, or from a performance standpoint, where the application just uses the data in a certain way, and the system's like, perhaps I should move this to fast storage, and it does that for you as well. People will take advantage of resources that you give them, or a certain kind of person will take advantage of the resources that you give them very specifically and intentionally, but often, for the general case, it needs to be something that's automated.
Sylvie, hey. Hi. I've been looking forward to a webinar about this. Yay, perfect topic. How do you know if an application needs a fast, low latency interconnect like InfiniBand, or more memory, or more cores? This is a good question. I think, Gary, you know the answer to this because you've probably come up against this.
Yeah, but I probably could use help from other people too. But yeah, I mean, you have to just run benchmarks and test it. And so usually, if it's a core memory thing, that's something you can usually figure out on a single node run. And then, but then if you start running multi-node, then that's, I mean, this is just a very simplistic answer, but if you're running multi-node and there's a lot of communication, that's going to show up in the benchmark when it doesn't perform as well, and it could be due to the fact that you have to go outside the node, and that's when a low latency interconnect will make a big difference. But it's really a matter of benchmarking the code. What's usually nice is if you can run the code somewhere, if somewhere where the code runs well. Then you can try to look to see where the performance differences are between what you currently have and where it runs well.
Yeah, needing more memory is relatively easy to discern. But Gary, you mentioned earlier that you maybe more recently have seen issues with memory bandwidth, and that being a bottleneck. How is that? How do you discern that when you're benchmarking a code? What are you looking for there?
Usually, people can try running on different nodes where there's different amounts of different number of cores and different speed and different memory bandwidth. So for example, we were able to just figure out one because it had different memory bandwidth speeds on two different nodes. What we would do is this is kind of thinking about scalability, is that we're thinking, okay, we don't have enough money. We want to buy as many compute nodes as we can. But maybe one way we can do that is that we can buy it with the memory half populated, and we'll buy larger DIMMs. So rather than say getting so we'll get like the DIMMs are going to be twice as big to get the same amount of memory, but we won't populate all the DIMM slots. But then by not populating all the DIMM slots, then that means that we're not going to get the same memory bandwidth out of that node. And so we had somebody that said, oh, my code seems to run slower on your new nodes than the older ones. And it was because the memory bandwidth was essentially, about 60% of what you could get out of one where you had all the DIMM slots populated. So what we did was we just populated the DIMM slots, and it bumped up the memory bandwidth, and then the person reran the code, and then they said, oh yeah, that runs fine now. But it was kind of one of these trade-offs where we wanted to essentially scale out as many nodes as we can with the possibility of adding more memory later. And then someone noticed like, oh, that's doesn't perform as well on their particular code and until we actually got to full configuration.
Awesome. Great answer, you guys. Thank you. All right. So I have been notified we've got 3 questions left. So let's do it. Let's get all these questions answered. Okay. Oh, I'm going to do my best to pronounce your name. Peter? Peter?
Peter. Yeah.
Peter? I like it. Okay, good. What tools are used to build a small HPC cluster and scale up?
And yeah, and in various capacities, we would point you to Werewolf for that in most cases. There's a lot of history behind the project, a lot of experience in building it up. We think it's a pretty good example of best practices right now, and yeah.
Yeah, I love that. Maybe a little Aptainer in there as well.
Yeah, but that's not so much in building the environment. That's how you would then run things on it. So absolutely. But in terms of how to build up that environment, start with Werewolf, and then you can then run things without a containerization solution. But there's a lot of benefits to just starting out the gate with containerized applications for sure.
Yeah, awesome. Okay, Sylvie, great. Also, how does the use of containers affect scalability?
So the only thing I'd say here is there are some challenges to be overcome. Just again, it's more of a cultural issue on doing distributed memory computing in containers. We've had a lot of success with that recently, but there's a documentation issue of getting that information out there and helping people to run MPI applications with Aptainer. That's something that's made easier in Fuzzball, but is possible even without it. But from like a performance perspective, there shouldn't be anything. Gary, have you seen any limitations or concerns with trying to scale containerized applications out, through any overhead or anything like that, or other issues that you've had?
No, we have, we've had people to move to, as people are doing more and moving to more Python-based codes. With the initialization of all the files and everything, that was hitting our file system really hard. And for a while, we were telling people they should containerize it, because then all the files are all contained in the container, and then that actually eased up the load on our I/O system quite a bit. So it allowed us to scale up more by having people move to containers.
Awesome. Oh, MB, what's up? Are you seeking disk I/O being less of a limitation these days with the flash disk arrays and these faster interconnects?
Gary, have you got Flash I/O at your site?
Yes. Yeah.
Yep.
So yeah, we put in we put in a VAST system. We put in a few of these, and they're all flash, and they work really well. And it does solve a lot of problems. I don't think that just the fact that it's flash by itself is necessarily the thing that makes the biggest difference. The system matters also. So that, because we've had other flash systems, and so it's a combination of things for the I/O that makes it faster. As people are going to start to be doing, now everybody's interested in doing these large language models, and they're going to require a lot of I/O, and the interconnect is going to, the path between the I/O, with the interconnect, that's all going to be really critical. So, not just the flash itself, but you're going to want to look at the system, the interconnect, supporting things like GPU Direct. Those are all going to be really critical coming up.
Yeah.
Awesome. All right, I think we're pretty much up. Oh, Sylvie, one more. Okay. What do others suggest for data collection and monitoring at scale?
I don't know. I've never been happy with my monitoring solution. It's always
Ryan, you got a good one?
It was
What do you
just
guys use?
Fuse
Gary?
Grafana, like Datadog, I guess, was one that I've used in the past. All, I think, yeah, that's just from my experience.
Okay, Gary, so you keep saying get the data. How?
Yeah, Grafana, Prometheus, yeah. But
Yeah.
probably more important is that you do something with the data than you just
Okay.
get it. Everybody gets, a lot of people get stuff and they get lots of data and they don't do anything. They never look at it. So make sure you do something with it.
Do something. So do those programs that you were just saying, do they analyze it at all for you as well, or they just gather it for you?
It's mostly gathering. You have to take, you
Yeah.
have to look at it. You have to go back and look at it. And that's where the real work is, I think.
Yeah, Grafana gives you the tools to look at it, but it's still a human process to derive meaning from all that data that you collected.
Yeah.
Yes,
It doesn't
that
do
is-
any good if you just gather it all up and then file it away on some disk and nobody looks at it. That's, might as well not do it.
Yeah, I think that's kind of what I do with my budget.
Yeah.
I gather
maybe
all
the
the
thing-
data.
The thing to say here is to take the problem seriously. Like as your system scales up, so does the data generated from it, just as an operational concern, and you have to treat that with the same, with the same weight and the same value that you do the applications running on the system. There's work to do there.
There is work to be done. And as Jonathan, you were saying earlier, we're happy to help you, right? So if you cruise
Other
over
people
to,
with better monitoring ideas than I can help you with CIQ.
not Jonathan.
And I'll be learning right along there with you.
Okay, awesome. So yeah, if you go to our website, ciq.com, you can get lots of information. It's easy to contact us. Just send a little note through and I will get it and I will reach out and we'll figure out whatever it is that you need and how we can help. I mean, a lot of the stuff that we talked about today is open source, so you can go play with it. Werewolf is open source. You can access it on our website. You can Google search it. So is Aptainer, same thing. We do provide the professional support behind that. We talked a little bit about Fuzzball today. So, we got some little ears tingling of like, ooh, what is this? So definitely reach out to us. We would love to have you, see you, help you, support you, hear what you're working on. And if you have ideas about future webinars that you really want us to address a topic, let us know in the comments. We read all of them. So like, subscribe, share with your friends. We love you so much. Thank you so much for being here. Have a great day. Bye.